I think this should be up and working. Let me just double check for a sec. Fine. Shin'ya, are you good to start?
Yes.
Fantastic. All right. Thank you, everyone, for joining us today. Today we have Shin'ya, who's going to join us to talk from entities, who's going to talk us about informative training free and task-agnostic inherently interpretable models based on pre-trained vision language models. Okay. So yeah, please take it away.
Yep. Thank you for kind introduction. Hello, everyone. I'm Shin'ya Yamaguchi from NTT, located in Tokyo, Japan. I'd like to thank the organizer for giving this nice opportunity. Today, I'm going to talk about our recent works on inherently interpretable models based on vision language models. I'm sharing the slides on this QR code, so please scan it if you want it. You can also access it through my personal page. So let's move on. Here's an overview of today's presentation. We focus on challenges in concept bottleneck models, CVMs, which predict final answers through the intermediate concept predictions. In particular, we show three new models to address the CVM's challenge in expressiveness, training cost, and task constraint. First, we show XBMs, which provide a natural language explanation as a rational of output. Second, we present ZCBMs, which perform interpretable classification in a fully Z-shot manner. Lastly, we introduce RVM, which provide a meaningful rationale for any visual task beyond classification. Here is the outline. I'll first describe background regarding CBMs, then present three works in order. Let's move on the first part, reviewing the background of inherently interpretable models and CBMs. The primary motivation behind this line of work is the well-known trade-off between the performance and the interpretability of deep neural network models. Although modern deep neural network models, DNNs, achieve exceptionally high performance, they are fundamentally less interpretable because naive DNNs cannot tell us why certain prediction was made. For example, given an image of links as input, if a naive DNN incorrectly predicts a lion, it just gives us a wrong answer, and we cannot understand the underlying reason behind this failure. To improve the interpretability, a common approach is to provide explanation by visual attribution maps, like GradCam. These methods visualize the pixel level contribution to the final prediction directly within input space as a heat map, like this. However, critical limitation is that they hardly provide any semantic meanings for those highlighted regions. So even if we see the attribution map for the incorrect lion prediction, it's still very difficult for humans to grasp exactly why the model failed. So to address this limitation, concept bottleneck models, CVMs, were introduced as inherently interpretable models that utilize intermediate concept prediction for the final output. Here, our concept is defined as the semantic ingredient of data, which is typically provided by human annotators. CVMs ensure interpretability by two stages of input to concept and prediction, input to concept prediction and concept to output prediction. So because final output is predicted strictly based on the predefined concepts, using a known phrase like Savannah, we can clearly understand and guess the reason behind the model's output. Recent advancement in CVMs built upon foundation vision language models, VLMs, like clip encoder. This integration enables the model to learn the input to concept mapping without requiring any manual concept annotations. Instead, they embed LLM-generated concepts directly into a multimodal text encoder. Notable examples in this domain include level-free CVMs from ICREA 2023 and DN CVMs from ECCV 2024. Despite their success, conventional CVMs still face three critical challenges, which lead up to our core research question. First, they suffer from the limited expressiveness of explanation because they strictly rely on predefined set of concepts, which severely restricts the vocabulary for rationals. To solve this, our first question is, can we provide natural language explanation beyond simple concepts toward informative explanation? Second, there is an issue of additional training cost. Standard CVM require training based on the label dataset, so it incurs massive data correction and GPU computation cost. That's our second research question is, can we build them without any target dataset and training? Lastly, they have a strong task dependency, meaning that the CVM's applicability is restricted to its specifically run task like classification, resulting in limited transferability to unseen tasks. It's related to our third research question. Can we build inherently interpretable models available for any tasks? In the following section of this presentation, I will introduce our three distinct works that successfully address each of these research questions. Let's move on to our first proposed method, explanation bottleneck models, or XBMs, which was presented at AAAI 2025. As I mentioned earlier, a major challenge in CVM is the limited expressiveness of their explanation. Since they strictly rely on specific predefined concepts, the vocabulary for rational explanation is restricted. One can consider increase the concept number to enhance their expressiveness. However, increasing the number of predefined concepts makes the training difficult because of the long-tailed distribution, and providing too many concepts actually makes the model less interpretable for human, as shown in the previous work. However, so increasing the concept may not be a solution to this challenge. To overcome this challenge, we propose explanation bottleneck models. The key idea is very simple, which is to provide rational explanation in natural language. XVM first generates a text explanation from the input image and then predicts the final label based on this generated text. This ensures the interpretability by the causal relationship between the explanation and the final level, output level. To achieve this, we leverage a strong pre-trained vision language encoder-decoder model, such as VLIP. For the training of XVMs, we optimize the vision encoder and explanation decoder and final classifier via target task classification loss combined with an explanation distribution loss, which is a regularizer. By utilizing Gamble softmax in this operation, we can maintain an end-to-end differentiable pipeline. However, a naive optimization using only classification loss causes the text decoder to ignore the structures of natural language, leading to the broken and meaningless output text. To prevent this, our idea is to penalize model's distribution by keeping it close to the pre-trained model's distribution using the KL divergence penalty term. This penalty term is efficiently approximated by a sequence-level nudge distribution without back propagating through all sampling processes. Once trained, XPMs provide 3 styles of explanation. First, the explanation text itself generated by the decoder. Second, concept phrases generated from the text using an NLP parser. And third, cross-attention map, heat map in the classifier to visualize which word contributes to the prediction. In our quantitative evaluation, XPMs outperform interpretable baseline label-free CBM in both accuracy and interpretability. So here, the CRIP score indicates the similarity between image and concept. So higher score means more related image-related concepts. And the GPT-2 perplexity means the naturalness of explanation. So this score is lower. It's this score lower. So lower is better. So additionally, our aberration study confirms that the explanation distribution loss is very crucial to avoid explanation collapse. Looking at qualitative results, we can see that XPMs focus on more detailed information to classify levels. The explanation distribution plays crucial role in ensuring the sanity of output, providing much richer human-readable rationale. If we discuss this explanation distribution loss, the model often outputs meaningless and not interpretable explanations. This slide shows how the generated explanation evolved during training. As optimization progress, the model successfully learned to gradually focus on the detailed feature necessary for the target task. In this example, the model gradually focused on important feature to classify California girl, like beak, ear, and mouse, which are the very important visual feature to classify this class. To summarize this section, XPMs successfully generate natural language explanation without relying on predefined concepts. By parallelizing the text encoder through explanation distribution, we ensure the quality of the generated text, and our experiments confirm that XPMs provide accurate and high-quality rationale both quantitatively and qualitatively. For more details, please see our paper and call repository. Now I will introduce the short concept bottleneck models, which will be presented at ICME in this summer. The main challenge we address here is additional training cost of CBMs. CBMs require target task training with concept annotation to learn both the input to concept and the concept to output mapping. Although we can avoid manual cost annotation by using LLMs or VLMs, they still require level target datasets. This leads to our question: can we build CBMs without any target dataset and training? To answer this question, we propose their short concept bottleneck models. The key idea is to combine VLMs and large concept bank for the short inference. This model provides input to concept and concept to output predictions via 2 main steps, which is concept retrieval and concept regression. The concept retrieval searches for candidates from millions of concepts, and the concept regression estimates the concept contribution by a sparse regression, like lasso. In the first step, concept retrieval, the model retrieves the top K concept candidate directly from the input image to handle the massive scale of the concept bank. This process is supported by an efficient vector search engine, such as FICE. Next, for the concept to output inference, we use concept regression. We select essential concept from the candidates and estimate their contribution by applying sparse regression, such as lasso, as a coefficient. So this step is crucial for reducing the redundancy in the predicted concept, because our concept bank contain many related concepts each other. So this process is very crucial to choose the essential concept by sparse modeling. This slide shows the overall inference algorithm of these CVMs. The final prediction is simply made by computing the cosine similarity cosine similarity between the label text vectors and the weighted sum of concept vectors. Yeah, it's very simple. We evaluated the concept quality of the CVM at first. The results show that the CVM can predict valid concepts that related to the input images. Specifically, they achieve higher C-grip score, which is similarity between image and concept, than training-based CVMs, like CDM. This indicates that the CVM generate more image-related concepts. For concept recall evaluation, which is coverage of ground truth concepts, it demonstrates that sparse regression is a key feature for providing effective concepts, because using linear regression as an alternative largely degrades the performance from the lasso in CVMs, in these CVMs. Moreover, these CVMs show sensitivity to intervention in concepts, confirming the model is strictly based on the content of concept. If we delete the concept, it gradually drops the performance. And if we inserting ground truth concept, it also gradually improves the performance. So it's characterize the sensitivity of the CVM to concepts. Looking at a qualitative evaluation, we can see that the CVM focus on various concepts in input images. Here we show the CVM with linear regression and the CVM with lasso. So the application of sparse regression successfully contributes to reducing the redundancy. For example, by cleanly handling multiple similar concepts about a code in this example. So with linear regression, the CVM outputs very duplicated concepts. But with lasso, it successfully reduced these duplicated concepts and choose essential concepts in their output. In terms of classification performance, the CVM achieved competitive performance to training-based CVMs. Furthermore, the model performs stable on any backbone VLMs like DFN and OpenGrip and Grip. We also found that choice of concept bank is crucial to achieve better performance. So the coverage of the concept is very important for task accuracy and interpretability. To summarize this section, the CVM successfully infer input to concept and concept to output mapping through concept retrieval and sparse concept regression. The predefined VLMs and the concept bank and sparse regression are keys to this approach. This work opens up a new problem setting, and these CVMs can serve as a good baseline in this zero-shot setting. Finally, I will introduce our third work, relational bottleneck models, or RBMs. This is very ongoing work, and I'm introducing this for the first time today. Before diving into RBMs, let's review the remaining challenge of CVMs: expressiveness and generalizability. Conventional CVMs use isolated concepts, making it hard to capture the semantic relationships. Although XVMs use free-form text, and it lacks semantic structures originally and not guaranteed to extract such relationships by NLP parser. Moreover, while ZCVM alleviates task dependency, they are still limited to discriminative task-like classification. So the CVM's generalizability is still restricted. This leads to our question: can we build inherently interpretable models available for any tasks with semantically structured rationals? The key to answering this question is a recent success of large vision language models, or LVLMs. LVLMs are LLMs extended to accept image input. Through post-training on diverse vision language datasets, they have shown emergent short reasoning capability for unseen visual tasks. Furthermore, this reasoning capability can be enhanced by chain of thought prompting or COT. So we can expect that LVLMs have expressiveness to generate semantic structured rationals for our purpose. Based on this LVLM's capability, we propose a novel inherently interpretable model called relational bottleneck models, RBMs. RBMs have three key features. First, they use relations as rationals to directly represent the semantic rational relations of concepts in images. Second, they offer zero-shot interpretability for any task powered by LVLM reasoning capability. And third, they are plug-and-play, meaning that we can convert any LVM into an interpretable model without additional training. The design of RVM is based on a two-stage inference strategy. The first stage is structured rational generation, SRG, which generates rationals as triplet of subject, predicate, and object. The second stage is rational grounded decoding, RGD, which forms the next token distribution of LVLMs through an ensemble of triplet conditional distributions. At the first stage, SRG, instead of using isolated concepts like cat in CVMs, RVMs represent rationals through the semantic relation between concepts such as cat, stand on, bench. This corresponds to subject, predicate, and object. We use a special instruction prompt to generate a set of these relational triplets along with their self-valorized relative importance scores, which we will use later in the decoding stage. In the second stage, RGD, we derived the next token distribution based only on the generated triplet rationals. Importantly, we discard the original image input from the context here. This strict information bottleneck ensures inherent interpretability, as the final prediction is completely grounded in the intermediate rational triplets. So, as a good news, we can compute these K logits for this power expert ensembling can be computed by batch parallel inference on GPU. In our experiments, we first conducted an implementation analysis where we replaced the generated rationals with ones from teacher algorithms here at Gemini 3, or randomly sampled rational for another query here, lambda. So the Gemini 3's rational represent better quality rationals, and random rationals are worse quality rationals than self-generated rationals. So higher is better in using Gemini 3, lower is better in using random rationals. These results show that RVMs achieve strong causal dependency on the rational content. That is, better quality rationals by Gemini 3 lead to better performance like this. And worse rationals by random rational lead to worse performance, showing that RVMs actually base their decisions on the provided rationals. Qualitatively, RVMs can describe accurate logical and semantic relation corresponding to the final output, providing structured and highly readable justification for their prediction across various tasks. For the left-hand example, RVMs successfully outputs rationals specifying the semantic relation of visual concepts like a pancake is located near fork, which is directly connected to the final answer pancake. More interestingly, for the right-hand example, our RVMs can generate logical stepwise triples to identify the final ground truth answer Goya, containing detailed information such as the image depicts a sleeping man, and then the man surrounded by bats and all, which are identify the artist of this work. Regarding the short performance, we evaluate RVMs by diverse tasks from general VQA, OCR, capturing, and complex reasoning task. Here, RVMs achieve higher accuracy than existing LVLM-based CVMs on almost all tasks. But we also observe that they are still inferior to direct or COT baselines that use the original image to answer. This highlights that accuracy interpretability trade-off and limitation of imposing the strict information bottleneck by RVM. To summarize this section, RVMs provide task-agnostic interpretability based on LVLMs by generating semantic triples as rationals and predicting answer from them. While they improve interpretability from LVLM-based CVMs, some limitations remain, such as accuracy drop from black box baseline and imperfect causal dependency on rational due to the nonlinear transformation in LVLMs for answering final output. Now let's move on to the final section on conclusion and future work. To summarize, we have three we have presented three distinct works that go beyond conventional concept bottleneck models by leveraging pre-trained vision language models. First, XBMs provide flexible and informative rationales beyond simple concepts through natural language descriptions. Second, ZCBMs perform interpretable classification in a fluid short manner without requiring any target dataset or additional training. And finally, RVMs achieve task-agnostic interpretability by generating semantically structured triplet rationals. I hope these three works give some perspectives to the research community for paving the way to develop practical interpretable models. Even so, several remaining questions point toward future works. First, regarding the performance drop compared to black box model, as we seen in RBM's work, we needed to explore how to achieve a better trade-off between accuracy and interpretability, or design entirely new architectures for high-performance interpretable model. Second, we aim to extend these frameworks to other modalities, exploring if we can apply them to minor or rare modalities such as time series data, or ultimately build interpretable models that accept any modality input. Lastly, looking from different perspectives from LLMs and agents, there's a critical question remain. Is an LLM reasoning such as Shin'ya method truly interpretable? And can LLM-based agents safely make contract with humans? How can we formally define consensus between humans and AI? I believe that answering these questions advances not only research community of interpretability, but also the relationship and collaboration between human and AI to the next stage. That concludes my presentation. Thank you very much for your time and attention. I will be happy to take any questions you may have. Thank you.
So much. Yeah, that was super interesting. I'm really happy about the last one as well, because obviously it's always fun to hear work in progress. Do we have any questions? I saw Oscar raising your hand. I'm not sure if that was a Mayan accent or not. Let me know. Otherwise, if anyone has a question, please feel free to unmute or raise your hand.
Hello, can you hear me? Yes. Probably. Okay. So thank you very much, Shin'ya. Just one question on actually two. They're both on the topic of interventions.
Intervention.
Yes, regarding the first paper that you mentioned, I was wondering, I may have missed it, but can you intervene with on the model when it's constructed in that way? How would you preserve the nice property of actionability of CBMs when the explanations are structured in this way?
Yeah, the first question, the answer for the first question is yes, we can intervene to the XBM, because the classifier is trained to infer the final level output from only on the explanation text. So we can change the explanation text arbitrarily by human and or somehow. So we can intervene to the explanation text. So the output actually improve or degrade by the based on the explanation quality. So the second question is about how to maintain the quality of explanation like CBM by this.
Kind of related. I mean, like it is very easy to intervene on a very standard CBM because most of the times you just have to change one value. Another, in general. But here, it looks like you can intervene in many different ways. The way you shape your explanation, it's kind of arbitrary. And I was wondering, in the paper, if you explored like quantitative ways on like how do you measure the impact of explanation of interventions here?
It is connected to the limitation of XBM. So the one challenge is the explanation is not structured like CBM. The CBM have the isolated concepts and the corresponding scores, so we can easily intervene to them. But here we have only text explanation, so we cannot know how the intervention affects to the model, obviously. So this is a limitation of the XBM. So it is difficult to control the intervention and the quality of the output by in this model. So this is also because this is also the reason why we introduced RVM. In RVM, we have structured rational. This make very us very easy to intervene to the rational because they have structured rationals and the corresponding scores, so we can modify the concepts in the semantic triple and the score, corresponding score, so we can easily intervene here. But in XVM, we it is hard to strictly control the intervention.
Have you tried by any chance if a prediction was wrong in XBM? If a prediction was wrong, just you provide a different explanation and see if you can flip the label, just by curiosity.
Yeah.
You flip the label by providing your own explanation to the image.
Yes. I try to intervene by ground truth caption for the for the task, and it actually improves the model's performance. But if we intervene by random swapped natural language text, so it significantly degrades the performance. So it's it confirms the sensitivity. XVM.
And just a quick question on this third one. It's still on the intervention thing. You mentioned it, but I didn't get the details of here. What you intervene on, and how can you, and what do you measure precisely? Like, do you intervene on the triplet? On the whole triplet, just one of the
whole triplet. We can actually intervene to one triplet, but we didn't. We haven't tried yet. Here, our intervention is defined by the intervening whole triplet of the for one query. So
all triplets, because you can intervene on a single triplet or a single value inside a triplet and see that maybe you can.
We can, but we haven't tried yet.
Okay, fair enough. Thank you very much.
Thanks.
Questions? I have a question regarding the sort of language aspect of this. So, for example, in the zero shot ones, you have this sort of lasso selection for the concepts, so to avoid redundancies, right? Which makes a lot of sense. But there's another sort of kind of redundancy that in this case would probably count as a shortcut, which is that some of these concepts could encode the class itself, the task itself, at which point the explanation becomes not that useful because if you encode the task with if you explain the task with a synonym of the task, it's not that useful, right? How do you avoid that? Because like I can see avoiding exactly the task because you know the task name, so you can make sure that that's not in the concept bank for any of these methods. This includes also XCBMs, for example, or the relational ones. How do you avoid having synonyms of the downstream tasks that can work as shortcuts?
Yeah, so it totally depends on the quality of the representation space of VLM. So because it's very different how the model treats the synonyms in their representation space. If the synonym is clearly differently represented in the space, we can choose the appropriate concept by this sparse regression. But in the low quality representation space, we cannot distinguish them by this system because there is not so much similarity in the such representation space. It is answer for you. I don't know. I can.
I was wondering if you've seen this because, as mentioned, this could probably happen. I imagine this could happen with any of these three models, right? Like XCBM, the explanation itself can contain a couple of things that are very close to the class itself, or it could be exact synonyms of the class itself. I wonder if you actually see that. Do you see the model learning to do these shortcuts where it's just pretty much solving the class, it's solving the downstream task on the text itself? So at that point, the explanation is the actual answer. I was wondering if you've seen that happening, or you think it's not the case.
Sorry, let me understand your question correctly. So you mentioned about when we met the synonym in the concept candidate, it occurs optimizing to distinguish synonym cause overfit or shortcut.
Case, but also in the XCBM case, the XCBM could generate as one of the intermediate tokens of the explanation a synonym of the downstream task, right? So in both cases, you could have another point actually classifying the class. It just means finding those synonyms in the explanation, which is so the explanation is not an explanation. It's just it's a proxy for the downstream task. So I was wondering if in practice you see these models learning to cheat this way, because I find it interesting. I imagine that could actually be a quite common scenario where this model just learned that, oh, maybe I just encode the actual downstream task in the language itself and then let the and the XCBN more than in the because in the zero shot you have a consent bank, so you can maybe curate the consent bank and try to make sure that doesn't happen. But in the XCBM, I can see a very strong incentive for the model to cheat, to do these sort of shortcuts.
Yeah. It's also limitation of these XVMs and ZCVMs work because we cannot control the concept space by human annotation. So in conventional CVM, we can strictly design and ensure that there is no overlap between the output space and the concept space. So, but we actually use in XVMs and ZCVM, we actually use a pre-trained vision language models. So we cannot control strictly the concept space. So it can be occurred, in any case.
It seems like interesting as well for like future work as well, trying to understand how that can be elevated. But that's pretty cool.
So, but in RVMs, we define the semantic relation as a rational. So it's not simply it hardly calls a simple shortcut, because this is not just an isolated concept. If we use the isolated concept, it's maybe leaked to the output space, but it represents a relation. So yeah, there's different meaning of
This would actually be been
it's a
harder unless
different
the class
space,
is exactly the relation that you're learning, right?
yeah, but it's fundamental challenge of VLM based inherently interpretable models, I think.
Questions? I'll do a couple more and then we can finish. But in terms
Yeah.
of the RVM stuff, by the way, super interesting work. I find it really cool. How do you avoid then? So it's similar to the redundancies. Sorry to keep asking over it, but I'm curious about that. How do you avoid redundancies in the relations? So, for example, you could express something being you could express relative things like something is right
Yeah,
to
yeah.
something or something is left to something. And
Mm.
it's a redundant relationship, right? Like so the one object is left to the other, or the other object is right to the other. It's the exact same relation. How do you avoid them all learning these sort of tricky things that represent the exact same relationship just using different operations?
Yeah. It's a good question, and it is also depends on the LVLM's reasoning capability. So there is no restriction to avoid such uh, tricky things. So
Like, do you see that
yeah,
that
yeah,
happens?
yeah.
Yeah.
Sometimes RVMs generates very tricky laterals, but recent large vision language models have very sophisticated reasoning capability, and it can generate almost very correct visual relationship. So the most important thing is you just use a rationale to output the answer by power of expert ensembling rational condition distribution. So the important thing is, if the rationale is wrong or tricky, then the output is also wrong or tricky. So we can see the reason why the model generate wrong answer from this system. Yeah, this is not only limitation but also advantage of the RVM. I think, but yeah,
And the sort of the verbalization, just to make sure you understand, the 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 actual verbalization, is that dependent on the task? Sorry, if you go back to the previous slide, I think, or
previous right here. No,
so on the one where you talk about how the triplets are made. Yeah. So
yeah,
the server bias importance, is that task dependent or is that triple specific?
yes, yeah. It's task dependent. So the model tried to generate a triplet to answer a query or task. So it's totally depends on the query text queue. So yeah, here is a diagram. We first generate a triplet rationale from the query and the input image. So the model try to generate a triplet from image, both image and query. So it's totally depends on the what is the question in the query.
The actual
This poses also poses a limitation of this work in the capturing task. It's very hardly to represent the rationale to this task, because capturing requires more detailed visual descriptions. Yeah, we we only have 5 rationals in this experiment. So it forces model to focus on limited perspective of visual relationship. So it is difficult to generate much quality caption from the only the limited triplets. Yeah, it's limited.
And the actual relationships, are those like they come from a predefined set of possible relationships that you're allowed to do, or is the model free to put any as long as it's a binary relationship, you can use any relationship between the objects?
Yeah. So if you want to restrict the format of rational or relational triplet, you can modify the instruction prompt to generate some more binary or more specific predicate. So yeah, it has a flexibility to adjust the downstream task.
It's really interesting. I imagine this is a bit few shot. Like, do you give it examples in the prompt, or is it like actually?
Totally just shot. Yeah.
Amazing. Cool. Sorry, I'm monopolizing this sort of channel. So, does anyone have any other questions? Not. Then, yeah. Thank you so much. Yeah, this has been super interesting. We really appreciate it. Cool. All right, everyone. Thank you, everyone, so much for joining us. If you want to join us next week as well, we'll have it at the same time. It's going to be, I think, Simon Schroding next week, talking about selective concept alternate model. Feel free to join us. And thank you so much again, Shin'ya. This has been fantastic.
Thank you.
And we appreciate it.
Thank you.
Cheers.
Everyone.
Bye.
Bye. Thank you.